So this is our lesson for section 3.1. We're going to be talking about increasing and decreasing functions. So the definitions are there at the top of the sheet. A function is increasing on an interval if for any two numbers, x1 and x2, where we're assuming x1 is greater than x2, if that implies that f of x1 is greater than f of x2, then we are increasing on that interval. So in terms of a picture, if we have our xy axes and we say x1 is greater than x2, and if that's the case, and the function value of x1, maybe up here, is greater than the function value of x2, that would be meaning the function is increasing. So as long as every x1 greater than x2 means the function value of x1 is greater than the function value of x2, then that interval is an interval of increase. And for the same reasoning, if we had x1 greater than x2, but the function value of x1 was less than the function value of x2, then our function would be decreasing. So that's what you knew from algebra class, Math 22, Algebra 2, about increasing and decreasing functions. Now we're going to use calculus to test for areas in the or regions in the function where we're increasing or decreasing, or where we're constant. And the way we're going to do that is we're going to use our derivative. So if we have a differentiable function on an open interval a,b, then we will know if a function is increasing on that interval if the derivative in that interval is always positive. So for all the values between a and b, if the derivative is positive, the function will be increasing. Remember, the derivative measures the slope of the tangent line. Positive slopes of the tangent line make the function increasing, and they all lie below. If, on the other hand, the derivative is negative for all the values in that interval, then the function will be decreasing on the interval AB. So that would look like tangent lines that have a negative slope. Or if the derivative is 0 for all those values, we may have a constant function where the value of the function stays the same across the interval. So in terms of a picture, negative derivative means your function's decreasing. 0 derivative means it's constant. Positive derivative means it's increasing. And that's what we're going to use when we're testing in 3.1 for these different intervals. Critical number is something we're going to be talking about all throughout the chapter. Critical number in section 3.1 is that if the function is defined at a value c, so this is an x value, c will be a critical number of the function if one of these two things is true. Either the function's derivative, when you plug c in, gives 0 out, or the function's derivative, when you plug c in, is undefined. So c values, those x values that we're going to call c, will make the derivative 0 or undefined. So what we're going to do in section 3.1 to find these intervals where we're increasing or decreasing or constant, we're going to go through this 4-step process. We're going to find the derivative of the function, which is what chapter 2 is all about. We're going to locate critical numbers by setting the derivative equal to 0 and finding out where it's undefined, because both of those will create critical numbers. We're going to test the sign of that derivative for any arbitrary number in each of these intervals between our critical values, and use that test of the sign to figure out whether our derivative whether our function is increasing or decreasing on that interval. So it's always going to be a 4-step process, and then in section 3.2, we're going to go beyond that to talk about what happens when our function changes from increasing to decreasing or decreasing to increasing. But right now we're just trying to find places in where the function might change and make a note of that. So a picture of what we're talking about could look like, we start with a fairly simple example, a function that we know a lot about, y equals x squared. So the first step is we're going to take the derivative. The second step is we're going to see where is 2x equal to 0, where is 2x undefined. I've got to answer both of those questions, and the answer to this question is when x is 0, and the answer to this question is never. There's no value of x that would make it undefined. So what we just found is a critical value. So our critical value is 0. We're going to set up intervals from the left of the number line up to that critical value, and from that critical value on out. And we're going to check to see what's happening in our derivative in those intervals. So if we pick an arbitrary number in here, any number that lives in this interval, say the number -1, for example. If we plug the number -1 into our derivative, we get a negative number. If we plug a number in this interval, like 1, into our derivative, we get a positive number. We don't need to know the value of it, just that it's positive. And so what section 3.1 is telling us is our function is increasing on the interval 0 to infinity, because that's where the derivative is positive. It's decreasing on the other interval, -infinity to 0. We already knew that because we know what our function looks like. We know that the function is decreasing over here, where our x values go from -infinity to 0. It's increasing here, where we have the x values between 0 and infinity. We're using soft brackets because it's neither decreasing nor increasing at 0. And infinity and -infinity are not numbers, so we can't hard bracket them. So when we write these intervals, they'll always be with soft brackets. So sometimes a function might have multiple critical values, multiple places where the function turns around. And we'll have to find each and every one of them. So for example, if we have a function of x cubed plus 3x. When we take the first derivative, we end up with, I'm going to make this x cubed minus 3x. We end up with 3x squared minus 3. If we try to figure out where 3x squared minus 3 is equal to 0, or 3x squared minus 3 is undefined, because we've got to make sure we check both, we're going to get when 3x squared is 3, when x squared is 1, when x is positive or -1, and never undefined. So now we have two critical numbers. We have -1 and +1. So we're going to have to look at our intervals from -infinity to the first value of -1, and from -1 to 1, and from 1 on out to infinity. And I'm going to go get another pencil. Yeah, it's not working any better. Okay, so now on those intervals, I need to check the sign of our derivative again. This time we're plugging into 3x squared minus 3. So we need to pick a number that's in this interval, maybe like -2, plug it into our derivative, and figure out that that would be a positive value. Now we'll pick a number in this interval like 0, and we'll get a negative value. And our last interval, we can pick a number like 2, and because this is an even function, we're going to have the same result. Our derivative is an even function. We're going to have the same result. It's going to be greater than 0 again. So what that's telling us about our function is our function is increasing between -infinity to -1. Then it's decreasing, -1 to 1, increasing again from 1 to infinity. So it's increasing from -infinity to -1 and 1 to infinity, and it's decreasing between -1 and 1. And if you graph the function on your calculator, you would see it doing something like increasing, I'm looking at the function, -1 plus 3, so would it be increasing, and right around -1 it would start decreasing, and then right around 1 it would start increasing again. It would have that general shape. You could put plot points or draw it with your calculator to double check. But the idea being the derivative is telling us what the function is doing because of its sign. Positive derivative increasing. So for all of the problems that you're going to do in 3.1, you're going to go through those steps. Find the derivative. See if there's any place where the derivative is equal to 0 or undefined. Set up your intervals and check the sign of your first derivative. So the last thing that I want to mention is it might be that your function looks like x to the 1/3, let's say. So this function is a function that you can plug any value into because it's a cube root. Remember, it's the same function as that. But when you take your derivative, we end up with a negative exponent on our x, which I wanted you to turn positive in chapter 2. And the reason is when I go to find critical numbers, I want to figure out where y prime is 0 or undefined. Now I'm not going to be able to find any critical numbers that make this equal to 0, because the only way to make a fraction equal to 0 is make the numerator equal to 0. So I'm not going to get any critical values from here. There's nowhere that that derivative will be 0, but it will be undefined when x is 0. So 0 is a critical value it makes the first derivative undefined. 0 is also in the domain of the function. I'm allowed to plug 0 into the function. So when I go to create my intervals, I'm going to break up my intervals around that critical value of 0. I'm going to check the sign of my first derivative, which is this. But what I'm going to find is, if I plug a number like -1 in, this function is a square. It's a cube root and a square. No matter what I put in for x, I'm going to square it, which means that if I put -1 in, it's going to become +1. My derivative is going to be greater than 0 when I use a number like -1. When I use a number like +1, it's also going to be greater than 0. So my function is going to be increasing on this interval and increasing on this interval, but not right at 0. So if you think about what the cube root looks like, we'll see if that makes sense. If you plug in a number like 1, you get out 1. If you plug in a number like 8, you get out 2. Cube root of 8 is 2. If you plug in a number like 27, you get out 3. So it is creating that kind of a shape on the right, and because it's an odd function, it's creating this kind of shape on the left. You could pick points and prove it too, with -1 and -1 and -8 and -2 and -27 and -3, but that's the general shape of a cube root. It's increasing here, and then it increases again. So it's increasing. The tangent line goes vertical temporarily, then it's increasing again. So this function doesn't have any spots where it's decreasing. So the moral of the story is critical numbers can come from your first derivative being 0, your first derivative being undefined. However you get them, you create intervals around them. Check the sign of your first derivative to figure out what your function's doing there.